the magic numbers. Let me move this one down here. What is this here? Here we go. So we have reduced the magic numbers by having our harmonic oscillator, right? Our harmonic oscillator potential. Which has a potential, as we know, of 1/2 of kx squared. And to that potential, we added a perturbation. So basically, we have a Hamiltonian, which is given by our harmonic oscillator, plus a little perturbation, which was our spin orbit interaction. Right? So by doing so, we move our equidistant levels, the 0s, the 0p, the 0d, 1s. So basically, this, remember, these guys didn't change anything. These guys, there was a little splitting here that we calculated the other day. This 1s remains the same, but now it was 1s, 1/2, 0s, 1/2. This became 0p, 3/2. This became 0p, 1/2, where 1/2 is equal to small j. The total angular momentum of that particle in that particular orbit, right? So we know the Pauli principle allows only 1, 2, 3, 4 here, 1, 2, and here we have another 1, 2, and then this guy splits also onto the 0d 3/2 and the 0d 5/2. And here we have 6, 1, 2, 3, 4, 5, 6. And here we have 4. Again, our numbers, magic numbers, 2. Inside here, there's an 8. And here there's a 2, where there's enough energy gap for these nuclei who fill a shell. Remember, this is for protons, but also we have the same thing for neutrons. But the building is a little bit deeper because neutrons don't have the repulsive interaction between protons, right? So now we have like we can say, okay, that the magic number, a magic nucleus, can be helium-4 because helium-4 has 2 protons and 2 neutrons, right? Or it can be oxygen-16 because oxygen-16 has 8 protons and 8 neutrons, right? Or it can be 20 calcium because 20 calcium has, 40 calcium because it has 20 protons and 20 neutrons. So these nuclei are particularly stable. And so by adding this spin orbit interaction, we could explain the next magic number, which was 28, and the next one, which was 50, because here we have the next magic number was 40, right? So this was wrong. So basically, we are just summarizing what we did before. And we also say that this is a function of r, instead of having a 1/2 of kx squared. If we make it in 3D, obviously this is going to be 1/2 of kr squared potential, right? As a function of r. So this, as you can see, and this is an important point, this has, as you can see, for each r, we're going to have the same potential, right? So we say that we have a spherical symmetry, which will, with this simple shell model, will only allow us to explain and this is what I want to outline here, spherical nuclei. So this shell model that we have deduced so far is, let's call it the spherical shell model. So there's no doubt. Okay, and the spherical shell model will only allow us to calculate spherical shapes, or to calculate the nucleus, properties of the nucleus, which is spherical. So we need to understand very clearly the limitation of our model, right? And now we are going to start filling up those floors, those orbits, and we are going to infer properties of nuclei. Very simple. So basically, let's say we want to know the properties of, say, oxygen 17. So oxygen 17, let's make a building here. Let's call it oxygen 17. Which has 8 protons, right? And 9 neutrons. So we make the building, let's make the neutrons a little bit deeper. So we have here the now we are going to use already the one with the spin orbit interaction being included. This is for protons and this is for neutrons, right? So then next one comes here, 0 P3 half. As you know, the P3 half lies below the P1 half because of the spin orbit interaction when we did J equal L plus S, where J square is equal L square plus S square plus 2 LS, right? So once we solve this perturbation, remember, this will give us a different splitting of the two levels, where the one with J with a bigger J will come lower in energy than the one with a lower J. So the energies will be split for P, for instance, for D, but not for S. So we keep building our nucleus, and the same thing here, 0 P3 half and 0 P1 half. And we always remember there's a magic number here, there's an energy gap there, and there's an energy gap here, and then comes the next ones, right? And the 0 D phi half, then comes the 1s 1 half, and then a little bit higher comes the 0 D 3 half. And the same thing here, 0 D phi half, 1s 1 half, and 0 D 3 half. And now let's take a different color and let's fill up our guys. So let's make this a little bit bigger. Let me use this brush here. All right. So now we have 8 protons, right? So we're going to put 8. 1, 2, 1, 2, 3, 4, 1, 2. That's it. As you can see, we are quite stable because there's a large energy gap there. And now let's see what happened with the oxygen 17 with the 9 neutrons, right? We go to the neutron side and we have 1, 2, 1, 2, 3, 4, 5, 6, 8 total, and then 9. So here we have an odd particle. So we have an odd particle right here. which is going to define, as we are going to see, the nuclear properties. Remember, the occupancy is going to be given by 2J plus 1. So in this case, is J is here, 1/2, right? So the occupancy will be given by 2 1/2, 1 plus 1, 2, right? And this is because of the Pauli principle, right? No two fermions can have the same quantum numbers. So now let's look what happened. Let's look in particular to the case of oxygen 17. And for that, we go to Google and we just type NNDC, the National Nuclear Data Center. So we go there, Brookhaven National Laboratory, and we are going to this ENSDF. This is evaluated data, which will tell us all the information that we know of oxygen 17. And here we're going to just type 17 oxygen. 17 oxygen. We're going to search. We're going to select all. We're going to get a PDF version. We're going to copy here 17 oxygen. And you see, I'm going to put it there. Here we go. We're going to open it up. And there we go. Look, this is the information that we know of oxygen 17, right? So the ground state is a 5/2 plus. So now this is the energy level 0. This is the ground state. The nucleus is stable, and the ground state has 5/2 plus. So now let's look at our particular case, and our simple shell model has, this is equal to J, which as you can see is 5/2. But as you know better, the parity is equal -1 to the L. And we have S, P, D, F, so S0, right? 1, and this is 2 for D. So obviously we have a positive parity. So this is our J pi, where pi in this case is positive, right? So basically this odd particle here, this odd particle is determining the properties of the ground state right here, right? We have the total angular momentum for that particular nucleus, the ground state, angular momentum, and parity is 5/2 plus. And not only that, we can say, okay, let's erase this fellow from here. Let's erase with this one. And now we're going to promote this particle from there. We're going to promote it. It jumps from here. Basically, it was here before, and now let's write it down like this. Like it was there before, but now it is somewhere. Sorry, I have to make the to change to the brush, which is yeah. So basically, let's say that this particle jumped from here to there, right? There's an empty hole here, but the particle now is somewhere right there. So what is the properties of that particle now? the particle, that excited level, because it was in the ground state, it was here, but now has moved up there. Now, as we can see, it has a different angular momentum, and that angular momentum is given by 1/2, and S is also positive parity, right? S is equal to 0. So basically, the first excitation, the nucleus gets excited by moving this particle, which was here, has been promoted to the level above, the simplest case scenario. It's not always like this, because as we know in quantum mechanics, everything is a linear combination of these particular states that we have here, However, as we can see, the first excitation is an energy of 870 keV, and it's a 1/2 plus, right? 1/2 plus, as we have predicted, right here. So let's go by make this green. So then we have that for oxygen 17, the ground state is a 5/2 plus, experimentally determined. That's what the NDC is all about. It's all about experimental data. The first excitation is a 1/2 plus at whatever energy. We're not going to calculate energies, but we just want to know what is J and parity. We could also calculate energies, but let's forget about what there is 870 kV, whatever is the energy, we don't care right now. So then it tells us, look, it tells us that the next one is at 1/2 minus. Actually, let's consider the energy, because this energy now is a big jump, 3055, right? So here it was 870. Put the energy of the state here, 870. This is in keV. And then suddenly there's a jump here, and we have a 1/2 minus. And this energy is much higher, which is a 3055 keV, or 3.055 MeV, right? So you can see there's a huge jump here in energy. And let me investigate. Let us investigate actually together. Let's see if we can delete this. What have we done actually? Come on. All right. So we have that odd particle, which was there before. That odd particle, which was there before. Here we go. And we have this level that now we can write on top of that thing that we erased. Let me see. Let's make a new one. And let's just draw this quickly again. All right. So we have the 0 as 1/2, the 0 p 3/2, the 0 p 1/2. Up there we have the 0 d 5/2, and we have here the 1 as 1/2. Now there we have the 0 d 3/2, right? So now we have these particles. We have the one particle here, right? Maybe a little bit bigger. The one particle here. We have two particles here, We have 4 particles here, 1, 2, 3, 4, and we have 2 particles here. So basically, we are on the neutron side, and these are 4 neutrons. So we are only interested in the odd particle because for one particular reason that we haven't mentioned, wherever you have couples, they couple to each other and they couple to J equals 0. This is the property of a pairing, the pairing interaction, which we mentioned the other day. But basically, these protons, as you have, every time you have a pair, they will couple in these time reverse orbits, where they have very large overlap, and they are close to each other. So there's the short range interaction provides an extra binding when you to those 2 protons, 2 neutrons, and you need to break apart if you want to populate them. So all these guys are coupled with each other. So if you want to populate them, I mean, you want to excite them, you probably need to break a pair. Then you can promote a particle up there. So let's see what happens actually if we break this pair and then we move this fellow. We make it jump here, right? So this fellow is not here anymore. So now this guy obviously coupled, but then this fellow is not here anymore. So this remains as the odd particle, right? So the odd particle now is in a different orbit in the p1/2, but as we know, parity is equal to -1 to the L, and this can provide a negative parity because p is equal to 1, right? And we see in our nucleus in oxygen 17 that we are investigating right now that the ground state is a phi-half plus, as we have this particle was the odd particle before, right? This one here. Then the first excitation at 870 keV with respect to the ground state was this guy being promoted up there. And now we have a bigger jump at 3.06 MeV. And this guy is a 1/2 minus. And this 1/2 minus comes, as you can see here, is a very likely possibility that we have a J 1/2, P is negative. So we break a pair of neutrons in the 0p1/2. So basically you break the pair, and this requires some energy. And not only that, but you need to go over the magic number 8, right, which is here. So which add more energy as well, right? So we have double energy, one to break the pair and one to promote these guys here. So that's why suddenly you have this big jump to almost 3.1 MeV for the next excitation. So this is the ground state. This is the first excitation. And this is the second excitation. So this simple model of the shell model here, it will allow us to get what is the ground state, what is the first excitation, what is the second excitation, in a very simple way. As you can see, we have just drawn these guys, we just add them together. If they pair, we know that they add to J equals 0. And that's why any even nucleus will have a ground state of J equals 0. So even nuclei, the ground state will have J equals 0 plus, right? Because all these fellows are coupled with each other, right? However, in this particular case, we had an odd particle here. The 9th neutron was here because we have 8 protons and 9 neutrons. So the odd neutron is the one which is going to contribute to all these excitations. As you can see, the odd particle characterize the ground state and first excitations of nuclei. This is a very simple picture. In quantum mechanics, any of these guys, I'm going to change the color now, or I can maybe open a new one so you don't. So we have any of these 1/2 minus, 1/2 plus, 5/2 plus. Even for the ground state, the 5/2 plus, the wave function of that 5/2 plus will always be a linear combination of those states that we are discussing here: 0, d 5/2 plus beta, 0, d 3/2 plus gamma 1 s 1/2. And if we open up to the ones below, also, like delta 0p 1/2 plus whatever Greek word 0p 3/2 plus the other ones underneath. However, for mathematical purposes, sometimes we just use the top row. But as you can see, the top row, if we do that in what is called the ASD shell, right? If we do they use the D and the S here, right? The D 5/2 and the S 1/2 and the 0D 3/2. These guys are L equals 0 and L equal 2, which positive will always have positive parity, right? So if we do that, if we take the 5/2 plus as a linear combination of these 3 guys on top, we won't be able to explain any states with negative parity. To include states with negative parity, we need to go down here to the 0p 3/2 and the 0p 1/2, which is called the p shell. But this one also won't have any negative parities, because these guys, the parity allows to have a negative parity, and this is why we have a hint that in the oxygen 17, this 1/2 minus, actually the origin of this 1/2 minus comes from the p shell, right? The 5/2 plus comes from the SD shell, and the 1/2 plus also comes from the SD shell, right? Promoting this particle here, or breaking a pair of particles here and bringing it right here, where the odd particle was in the first place. So then the remaining particle is only right here, right? So basically, the odd particle again characterizes the properties of nuclei. And tomorrow we'll see this that there's a separation of the energies of a single particle generally are much larger than the energies of the frequency of the single particle are much larger than the frequency of the whole nucleus. And we'll see that in the Nielsen model when we introduce it tomorrow. But for today, I want us to play around. Now, okay, let's go and see a different nucleus. Let's ask ourselves what happens with oxygen 19, right? What happened with oxygen 19 or with fluorine? Let's see. Let's look at the nuclear chart and let's see what is CD documents. a grid chart of nuclides. And let's look what we have here. Let's see. See what we have. So we have calculated oxygen 17, oxygen 18. The ground state will be 0 plus, as I say, all even nuclei. Oxygen 16, 0 plus. So what happened with nitrogen 15? Let's see what happened with nitrogen 15. It tells us experimentally is a 1/2 minus, right? The ground state. So let's see. So nitrogen 15 has 7 protons, and as you can see, 8. So the number 7 will characterize the number 7th neutron, and we are going to do it quickly. Will characterize the properties of nitrogen 15. Right. And again, we do the same thing. And again, we do the same thing where we have our 0s 1/2, our 0p 3/2, our 0p 1/2, and this is for protons. And a little bit down here, always remember that the neutrons are a little bit deeper in the energy, in the binding energy, because they have no charges. So 0s 1/2, 0p 3/2, 0p 1/2, and then the next one is the magic number 0d 5/2. Well, let's get it there because right. So then we start adding guys here. 1, 2, 1, 2, 3, 4. Say 1, 2, 1, 2, 3, 4. But we are trying to do 15 nitrogen, which has 7 and 8, right? So this 8, here that's it. 1, that was too much, too big. Make here 1 and 2, that's it, 8, right? So here, however, we have 6 and 1 is 7, right? That's the 7th. Then, as we have mentioned before, this 7th is the only odd particle. The J is 1/2 and P is 1, so that will give us a 1/2 minus, which is what we see in nitrogen 15, right? This is an odd nucleus, 7 and 7. Forget about those ones right now because those ones are more complicated. In those ones, anything can happen, you know. So we are interested in odd even nuclei where there is a odd even nuclei. There's an odd particle basically. Even as I mentioned before, there are even nuclei. The J initial is a 0 plus, and then we have some collective motion that we're going to study later on. We can also break particles and see what. But so far, let's focus on the single particle and this odd particle that is characterizing the properties of nuclei. Right. So now it's up to you. Now you start playing and say, okay, I want to try. Let's try fluorine. Oh, you see, fluorine 17. What would you expect from fluorine 17? 5/2 plus, right? Let's say as you add particles, let's see what happened in fluorine 17, oxygen 15, the same thing happened as for nitrogen 15, right? You also has an odd particle in the P 1/2. So you also have a ground state of 1/2 minus, as you can see here. So now you can go to the NNDC and say, okay, I want to study, or here in this chart of nuclei, we can go there and we just click on this germanium 87, which is a, but we can go and say, okay, fluorine 1, fluorine 17. So select all, PDF. See, 17 fluorine and NDC. So you open it, and here we go. The first excitation is a 5½ plus. Actually, very similar to oxygen 17. You see, 5½ plus, 1½ plus, and again a big jump, 1½ minus. So let's look at fluorine 17 quickly. Always remembering that fluorine 17, let's chart here. Fluorine 17 is here, which has 9 protons and 8 neutrons, right? So it's basically the same as oxygen 17, but we just exchange the number of proton and neutrons. So obviously, we're going to get the same result as we have oxygen 17. So let you do that, and I want you to start playing around and find mistakes. Find mistakes, because this is just a very simple. Everything works beautifully. But now is your turn to explore, right? So now you're going to say, okay, I'm going to look at the chart of nuclei. I'm not going to look at odd nuclei like fluorine 18. I can look at fluorine 17. Fluorine 17 is a good candidate. Neon 21, oxygen 19. You know, what happens with oxygen 19? So, and you explore and see whether what we have in our share model agrees or not. So as you can see, the whole picture has been summarized to something which looks extremely beautiful. You know, you take you just make your own building, right? 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, and you know, according to the Pauli principle, there 1, 2, say oxygen 19. We just fill up different inhabitants for each floor, 8 and 11, right? So there will be neutrons here. There will be protons here. So protons always are going to have 1, 2, 1, 2, 3, 4, 5, 6, 8. So that's it. For neutrons, we have 1, 2, 1, 2, 3, 4, 1, 2. That's 8. And then we have 3 additional guys here, right? To make it 11. So these guys, again, they will couple with each other. And then again, the odd particle will come with J pi equal 5½ plus, right? Because this first guy here is our D 5½, right? The next one is our 1s 1/2, and the next one is our 0D 3/2. So most likely this guy goes up there, or can also go up there, or maybe you break a particle, a pair of particles here, and these guys get promoted, they couple with this guy, and then the odd particle will give you a negative parity. So now, as I say, this subject is about exploration. We're just putting, according to the Pauli principle, we are getting all these guys, you know, first floor, only these 4 guys. Second floor, only these 2 guys. Fourth floor, all these 6 guys, you know. So what happened? Because for the 1, 2, 3, for the 4th floor here, which is the 0D 5½, we have an occupancy of 2J plus 1, and J is 5½. Obviously, this is equal to 4, so to 6. 5 plus 1, 6, right? So for the 0D 5½, we will have the possibility to have either 6 protons or 6 neutrons on the other side, 6 neutrons. And this comes from the fact that Hj comes with a bunch of Mj's, right? So if J is equal to 5½, so Mj will be equal to minus 5½ minus 3½ minus 1½ 1/2, 3/2, 5/2. So basically, all these possibilities will be available for that total angular momentum J. Right, which let's actually visualize what I mean by this, because tomorrow it will be important. So it means that the particle can have a rotation, which angular momentum J, all of them have angular momentum J. Actually, let's make this a new drawing because this is an important concept from quantum mechanics, and let's do it professional. So what are these? So let's see. So there's a particle. This particle may have a J equal 5/2, and as I say, MJ can be equal to plus minus 5/2, to plus minus 3/2, and to plus minus 1/2, right? So this can be minus 5/2, but always the J is always 5/2, the same J. But this is as the orientation is minus 5/2. Here, the orientation is plus 5/2. This is basically MJ, right? This is MJ. So now it can be 3/2, still the same orientation. So, but MJ is equal to minus 3/2, and the projection here is going to be that 3/2, right? The same thing here. We're going to have a particle, which it can be again always J 5/2, always J 5/2, but MJ is going to be equal to 3/2, right? The projection here is going to be equal to 3/2. So for the other guy, the same thing. We're going to have a J of 5/2, so the magnitude of the vector is the same, but MJ is going to be 1/2, basically. So the orbit will be something like this, right? This is the J is perpendicular to the orbit, and this guy will come with a projection here of 1/2. So basically, this is telling us for this guy which was pointing up there, the proton is or the neutron is orbiting like this, right? So you apply the hand rule, the right thumb rule, right? And then you rotate like that, and it points all the way up, right? So basically, and for this fellow, for this angular momentum, let's make it then the orbit would be a similar orbit because J is always 5/2, but now it will be somewhere here, right? So we have these three possibilities, and the same thing here. In this particular case that we are drawing up there, the particle goes this way. If we are with a J minus 5/2, then the particle goes the other way around. So basically, this will be very important for us to understand the complications that are coming in the next couple of days. So remember, it depends on the orientation. And obviously, depending on the orientation, you will have different quantum numbers which are allowed within the same orbit, right? Because we have different quantum numbers. So I'm going to stop here, and I'm going to ask for questions. So today was a very practical session, a very interesting one in the sense that you are applying what you know. You have reduced the harmonic oscillator, you have applied a little perturbation to the system, to the physics of the harmonic oscillator, which allow us to reproduce the magic numbers correctly. And now we have a new building, right? A building with gaps. It's not a building like we see around us, right? Like in the physics building where everything is not really equidistant because the physics building is a little bit bent like this, you know. And that's why I cannot open my door, room 204. Every time I go there, I have to go and push the door like I'm a thief. But besides that, normally in general, it looks like you have the same equidistant floors, you know, first floor, second floor. And this is not the case for the magic, for the shell model, right? In the shell model, we have one floor, the next floor comes very close, then the next floor, a big jump. So within all these floors, the Pauli principle allows these fellows to come in, or allows those fellows to come there, right? And there are precise formulation and mathematics for this to happen. So basically, you fill up the building with those guys which are allowed until you match the number of protons and neutrons that you have for the nucleus of interest. And then you see what is the odd particle. What is the odd particle? And the odd particle characterizes what is the ground state of the nucleus. This is a very simple model. As we say at the beginning, the 1/2 of Kr squared is for a spherical, has a spherical symmetry incorporated there. So it will allow us to explain nuclei which are spherical. So if nuclei are not spherical, the model will break down, and we shall see very soon. So question, guys? You must have some questions, because this is you have, with a very simple calculation, you can predict what the nucleus will be doing. This is something spectacular, right? What is the angular momentum? All these things have taken years and years, and many of them of the angular momentum are not known, right? So this simple model that we have calculated in a couple of days, hand waving, allows us to predict many things, actually. So, chat, any questions? Let's think about this for a couple of minutes, because this is okay. So,
excuse me, Prof. When you draw those states, the stages, for protons and neutrons, you always you always have an arrow in between the same binding energy going down. What is that? Meaning the energy is decreasing, or what?
right, I'm going to tell you that right now. We always must relate these things to our potential, right? So these things are inside our potential. So on our potential, let's look at this right now here. Make it big. So we have a harmonic oscillator potential, right? Which goes to infinity, which is not so good. This is VR and this is R. So what we are doing here is we are going, these guys, they are all here. So this is 0 S 1/2. This is the 0 P 3/2, right? 0 P 1/2. Then you have these three other guys, but they're all inside the potential. 0 D 5/2, right? There's a potential. It's a building which is within the potential. 1S 1/2, right? And 0 D 3/2. The others, that we can go all up to whatever. So these guys are our magic numbers: 2, 8, 20, right? So when I say that for neutrons, this whole structure goes down in binding energy, basically, I mean is deeper in the potential, because for protons, as we increase the number of protons, right, the Coulomb force will increase as we increase the number of protons. And obviously, for neutrons, this doesn't happen. So when I say this is a deeper building, we have a similar thing for protons and for neutrons. This will be, let's say this is for protons. But for neutrons, the building will be a little bit deeper, in the sense that you don't have, right? You don't have this, for the same level, it will be a little bit deeper, because you don't have the Coulomb barrier, right? So you don't have the Coulomb repulsion. So for neutrons, the same building, same orbitals, to be precise, but slightly deeper because there's no repulsion, right? Is that clear, Songeso? Everything is inside the potential. It's inside this potential. Well, here is negative, and if you go up there, it's positive, right? So here we will have a repulsion, and here we have an attraction. So that's what I mean. Always remember that we are drawing these buildings, but they actually belong inside there to be bound. These particles, these protons and neutrons, they need to be bound by this attractive potential. Stop sharing. Okay, so it's clear now.
Okay, Prof. It's a little bit clear.
But I like your participations. Okay, so I love when you ask questions. It's very important.
Prof.
It's okay.
When you say that the neutrons are a little deeper, do you mean that we don't draw the lines on the same level? The neutrons one go a little bit lower than the protons.
Yeah, basically, when we draw the shell model, we know that this one is going to be a little bit deeper, which is deeper because it's not, as you see, these are the protons, right? So if the more protons you add, the more for heavier nuclei, these levels will go up as well because they will be less bound. The repulsion, the Coulomb repulsion will bring them up, right? With respect to the neutrons, but they don't feel this repulsion. So obviously, in the shell model buildings that we are creating ourselves by adding the harmonic oscillator and the spin-orbit interaction, this building will be a little bit higher for the protons than for the neutron. But the same levels will apply, right? The same levels will apply, but the neutrons will be always a little bit deeper.
Is that due to the fact that the protons are positively charged and the neutrons are more neutral? So
right.
Because of the positive charge, that's where it comes in, and the neutrons are neutral, so
right.
It doesn't affect it that much.
Right. That's the reason why this is happening, right? So one is deeper than the other, but the same structure, because similar structure, because the protons repel each other because they have positive charges, and the neutrons are neutral, so they don't. It's just the nuclear force, right? There's nothing that stops the nuclear force. In the protons, you have a little bit of a increasing repulsion as you increase the charges, right? The positive charges. Good, Salman. More questions. Remember, this is going to be important for your participation mark. Craig, I've seen you have done a beautiful test. The multiple choice, you got 80% or something, which was it was a tough one. No? Do you think so, guys? What do you think about the multiple choice? I think most of you did okay, but I like that you have to think. You have to think and figure out your. Shoki, as the rep of the class, what do you think about the multiple choice? There were any issues, or what do you think?
I think I prefer the long questions. The multiple choice is just fine.
Okay.
Yeah.
Okay, but yeah. Yeah, the long question. The thing is that for the multiple choice, is a little bit of there's some hiding thing. You know, you also need to do the calculations, right? That's the point. But your brain it becomes lazy, and then you say, okay, A, B, C, D, E. So okay, I say E. But then also it also requires many times to do your own calculation, right? So you have to be with that eye of the tiger. When you have a multiple choice, don't think it's an easy one. Just think that you're going to calculate, and for the calculated ones, or when you have to upload the file, you have to calculate no matter what. So for this also, so that's why I always ask I always ask to provide, when you answer a question and in multiple choice, you have to provide a reasoning, right? Didn't you? Did you provide this reasoning? It's important that we provide the reasoning. Otherwise, I don't know why. I mean, you may have asked someone to what is this answer or what is that answer. I want everything to be 100% yours, right? So I will mark it. You have a mark, but I will reduce the mark if there's no reasoning behind the questions. Good, Songetso. So guys, today I recommend the following. We have lots of work for tomorrow. Tomorrow is the assignments, right? Okay. So we do it after the assignments. You can do all this, but it takes just half an hour. Half an hour, you go to the NNDC and say, okay, I want to investigate oxygen 19. I want to investigate neon 21. Something which is odd even, right? So, and see whether this simple picture, you start filling up your shell model and see whether this simple picture agrees with what is experimentally determined, right? In the NNDC. Okay, guys. If no more questions, I will upload this video in our YouTube channel.